Okay, second day of learning target 3. Last time we talked about dynamic problems where the sum of the forces did not equal 0. And then today we're going to talk about static forces, so that means all of the sum of the forces is equal to 0. And when the sum of the forces is equal to 0, Newton's second law tells us that the acceleration must also be 0. Okay? Now, we can graphically add vectors together to show that the resultant is 0. We have A vector, B vector, and C vector. So if I take A, and then I grab B, and I add on B, and then I grab C, and I add on C, well, the resultant is from the tail of the first to the tip of the last, but there's no resultant there. We ended where we began. And so that must mean that the sum of these forces all added together are equal to 0. Okay? Here's another way of looking at this. B can be broken up into x and y components, right? We can have b sub x, b sub y, and b sub x. Okay? And essentially what happened was A canceled b sub y, and C canceled b sub x. Because, right, this would be b sub x, b sub y. So see how we have vector A is going this way, but then b sub y is going that way, and they're equal in magnitude, opposite in direction, so they cancel. And then b sub x is going this way, C was going that way, equal and opposite, so they cancel. So the sum of the forces is equal to 0. Here's another way of looking at a similar concept. If we take A and B and we add them together, okay? So, ignore that. So if we took A and then we added it to B, well, the resultant would be from the tail of the first to the tip of the second, so our resultant vector is that direction, right? So if I were to draw this back in, if I were to show here's the resultant of A and B, and then I want to equalize this, I want the sum of my forces to be 0, well then I better have an equilibriant, which is the same magnitude as the resultant in the opposite direction. Because remember, this resultant is A and B added together. Okay, so if we get rid of those, then our resultant is right here. And so we better have a force that's equal in magnitude and opposite in direction so that the sum of the forces equals 0. Okay? And so drawing that in, this negative resultant, it's called an equilibriant. All right, so let's try this. Find the equilibriant for the following forces. So we have A and B. Okay, so we're going to take A, and then we're going to add B. I really should have drawn it up here. Sorry, let's move that. So we're going to take A, and then we're going to add our B vector. Okay? And our resultant would be from the tail of the first to the tip of the second. Okay? So there's the resultant. Okay? So if we have A right here, we have B over here, okay. The resultant is kind of like it's right over here. Okay. Okay, that's the resultant. And so our equilibriant would be the same magnitude, opposite direction. So it's our negative R. Okay, so that's the equilibrium. So with the equilibrium applied, so like if we add that now, what is the net force on the object? Well, the point of the equilibrium was for the sum of the forces to be 0. The net force should be 0. Okay. So how can two forces, 6 newtons and 8 newtons, be applied to an object to give a resultant of 10 newtons? Okay. Now, we don't know the angle between them. We just know that we have a smaller 6 Newton force, and we have a little bit longer 8 Newton force. Okay. Actually, let's draw this the other way. So we'll do 8 plus 6, which will give us this resultant. Okay. So how can two forces with 8 newtons be applied to an object to give a resultant of 10 newtons? Now I want you to notice something. Here's 8, and if I'm saying like that's 8 newtons and I pull that over, then our resultant is longer than 8 newtons. Okay? And so like how is that possible? Well, it all just depends on the angle between them, right? Or it depends on this angle between them. Okay? And we can do some math to figure this out. We don't know with a surety that this is 90. That's basically what we're calculating. So we could use the law of cosines. We could say that r squared is equal to a squared plus b squared minus 2ab cosine theta. Okay, and we could solve for theta. Okay, so this is subtracted here. Okay, so we could add it to the other side. Okay, and then minus the r value. So we could say 2ab cosine theta, which is added to r, but we're going to subtract that to the other side, so it'll be a squared plus b squared minus r squared. Okay. And then we can divide that by 2ab. So the cosine of theta would equal a squared plus b squared minus r squared divided by 2ab. And then if we want to figure out what theta is, then we just do inverse cosine of that. Okay. How could a third force be applied to produce an equilibrium? So if this is our resultant, right? So we have 6 newtons and 8 newtons. Very true. So this was 6 newtons. And we had 8. That was kind of going this way. And then our resultant was kind of over here between them. That should make sense, right? So there's our resultant. So our equilibrium would be same in magnitude, opposite in direction. So there would be negative r. Okay. So how could a third force be applied to produce equilibrium? Well, we would need that equilibrium. Add that equilibrium force, and then the sum of the forces will be 0. Free body diagram, static equilibrium force problems. Let's see where we're at on time. Okay, spend a few minutes talking about this. So, we can be working with a free body diagram, and based off of what it tells us in the problem, you can say this is a static problem, so assume the sum of the forces, not just in the x, but also in the y, are going to equal 0. Okay, so find the value of the unknown force here. Okay, let's set up this problem. We'll probably have to finish it on the next video. So I'm going to look at the sum of the forces in the x and the sum of the forces in the y. And a reminder, the problem told us that they're going to equal 0. Okay? So in the x direction, we have this force, some positive force, and then we're going to add that to the negative 75 newtons. Okay? And then that's going to equal 0. Okay? And so we can add that to the other side, and we can say our unknown must equal 75 newtons. Okay, nice. Look, we only had to look at our x components. So we didn't even have to go to the y. We could see, though, how they would cancel, right? We'd have a 125 newtons minus 125 newtons, and that would tell us the sum of the forces in the y are, in fact, 0. Example number 2, static problem again. Find the value of the unknown force. So our unknown force is right here. Okay. Now this unknown force is going to have an x and a y component, right? So we can have this force in the y direction and then the same force in the x direction. Okay. And look, we have another unknown. Okay. We have another unknown here that we're going to have to keep in mind. So we need to solve for both of those. Okay, where are we at on time? Okay, let's just set up the problem. Well, kind of like I said with the last one, we'll finish it next time. So we have the sum of the forces in the x direction, and then we have the sum of the forces in the y direction, and we know that they're equal to 0. Okay, in the x direction, I have a positive tension 1. Okay. And then I have a negative force of x. And those are my only forces in the x direction. All that's going to equal 0. Okay, I don't know this, and I don't know that. Let's look at y, though. In the y, I have a positive 9 newtons. Okay. And I have a negative 7.5 newtons. Then I also have a negative force of y. That's going to equal 0. Now this is nice because this is my only unknown. So that means that I can solve for the force in the y direction. And so we can take... let's, the simple way would just be adding that to the other side, right? So we have 9 minus 7.5, so that'd be 1.5 is equal to, and I added that to the other side, force in the y direction, right? And so we can lay that out a little bit more. We can say 1.5 is equal to the force in the y direction, but that was the hypotenuse, right? And y is across, so that would be sine 45, right? If I'm solving for that force of y, it's the hypotenuse, which I don't know, times by the sine of 45. Okay, so when we come back next time, we're going to figure out what this force is, and then we'll use it to help us over there.